this next portion kind of sort of tricks people up. We're actually going to be talking about how muscle contraction works, how is it going to be helpful, all that wonderfulness. So we talked about this already. We have a sarcomere here. We got the I band, which has thin filaments only. We have the H zone, which has thick filament space only. And then we got the A band. What this all means is that in this A band, these thick filaments and these thin filaments are interacting. The thick filaments, myosin, are touching and interacting with actin, the thin filaments. If we wanted to, this is a relaxed muscle. If we wanted to unrelax it, we need to do some work. We need to do some curls. We need to show off on how big burly our muscles are. We would begin contracting them, and how we contract them is these myosin heads start grabbing onto and pulling on this actin and pulling them inward. And as they do, it actually shortens these muscles. And as it shortens the length between where the muscle is inserting in its origin, it causes whatever part it's attached to move. You can continue to do so to a certain degree, but you will notice again that that I band and that H zone disappear. They're saying hi. Or when you relax, they say hi. And when you contract, they all close up. Notice the A band doesn't change in length again. It's always the same. Those myosin heads creep up that actin. Now, how does this work? How does this happen? Well, if we take a close-up look at both of these, both actin and myosin, you'll notice that actin, they made it colorized. They've kind of pointed out a couple of things. Actin has like a little black dot. In this drawing, it has a black dot. Myosin has kind of like, well, I don't know how to explain it. Maybe a broccoli, really weird broccoli-looking thing. Maybe a flower. Anyways, what's going on is myosin has myosin heads here. These myosin heads really like that black dot. And that's where they grab onto to make the creeping motion up and dragging these actin bundles further and further into that H zone. So problem is when remember there's that active site of actin, but in a relaxed muscle, this is what it looks like. What's the problem here? Well, I'll tell you what the problem is because you're not going to be able to respond anyways. There is this brown cord thingy here in the way of this active site, this site where myosin likes to grab. Myosin can't grab anywhere else on actin. It needs right there. It likes it right there. Well, let's give these things names because you know what? You're going to need to know. We got troponin. These blue dots are called troponin. And this brownish bar that we have going on here is called tropomyosin. It's called tropomyosin because, well, it's associated with troponin. And myosin because, well, it kind of likes, like myosin, likes to hang out in these active sites. So troponin, myosin, kind of like myosin. Like hanging out, well, that's pretty neat. Well, you gotta get this out of the way. And if you want myosin to be able to do its job. Troponin is the place that you have to have something interact with to make it move out of the way. You get troponin satisfied, it's going to make its boy tropomyosin move out of the way so that myosin can do its job. Well, there is quite the cascade to make this happen. And as you've just seen, it all begins right here. There's your muscle, there's some muscle fibers here, and then there's this structure here. This is a neuron. The neuron releases a bunch of, sends out terminals to each and every single muscle fiber. So a single neuron will interact with only a single muscle cell, a muscle fiber, to tell it what to do. In that muscle fiber, where they interact, at the very end of that axon, this is called a synaptic end bulb, by the way, there are little chemicals stored inside of it that when a signal goes zzz, coming on down, send out a signal, coming on down, sending a signal. Wow, that's a terrible song. It's copyrighted, you can't have it. So it comes on down, sends a signal saying, hey, boys and girls, we need to release some stuff out into this thing so we can make this muscle move. Well, we're not going to go into too much detail on how that works until chapter 12, or when we start talking about the nervous tissue. But all we care about is that these chemicals come out, and this particular chemical, that the only chemical, this is called a neurotransmitter, by the way, the only neurotransmitter, aka chemical, that comes from this neuron and interacts with this muscle, this neuromuscular junction, is called acetylcholine. It's abbreviated here ACH, but it is called acetylcholine. Acetylcholine, what happens, will leak out and interact and bind to receptors to allow sodium in. If you remember back in the good old days of AMP1, you remember that sodium really likes to hang out outside, and acetylcholine wants them to hang out inside. So it says, hey, boys and girls, I just opened the door for you. Come on in. And it lets it on in. And sodium just bum rushes it, which allows allows one really extremely important thing to occur, which we'll be talking about next. So again, acetylcholine gets secreted out, binds to its receptor, lets sodium in. But if we leave acetylcholine there, we're going to have some problems. We're going to have some overactive muscles. It's going to be tense. It's not going to be a happy place to be. Maybe you'll have some lockjaw or something like that. You got to clear out that acetylcholine. The neuron can reabsorb it. You could have acetylcholine esterase that's out on the muscle that actually breaks it down. Right, that breaks down acetylcholine. Or you could just have some macrophages, things in the immune system clearing it out. But enough of acetylcholine. Let's move on. Let's talk about what happens after acetylcholine binds onto these receptors. The receptors say, hey, it's time to let on sodium in. Come on in, sodium. Congratulations. You're welcome to this here muscle. And it lets that sodium in, and sodium goes, oh, what a great party. We should go to the sarcoplasmic reticulum. Oh, that sounds really familiar from the first video. That sarcoplasmic reticulum was important, wasn't it? I wonder why. So acetylcholine binds to its ligand receptor, which allows sodium in, and sodium comes in and finds this voltage-gated channel, voltage-gated meaning that it's sensitive to a different change in charge, says, hey, we should let calcium out of the sarcoplasmic reticulum. And it does. And it releases calcium. It allows calcium to surge out. And what's so important about having calcium in here and letting it surge out? Well, I'll tell you what happens. So again, sodium releasing that calcium. That calcium is the thing that binds onto troponin. Calcium is the key. This feels like a kid's movie that we're like trying to explore a mystery and figure it out. And we find out by mistake. And it's a miraculous wonder. Calcium binds onto troponin. And troponin goes, I really like that calcium. All right, myosin, it's good to go. You can play with actin. And it happens. And then you can have contractions, and it's magical and glorious and wonderful, and you can stretch it out. You can flex them muscles all you want now. Now, the muscles don't really want calcium hanging out in there the whole time, or you're going to have some problems with trying to get responsive muscles or fighting against each other. You know that type of stuff. So it's going to try, that sarcoplasmic reticulum is going to do its very best to pull that calcium back into the sarcoplasmic reticulum when it's not being signaled by this. And then it will return when that calcium is depleted. It releases that troponin. Troponin goes, oh, I miss calcium. Sorry, myosin, I'm closing down due to depression. And it closes it up, those actin proteins, so that myosin can't do it, and muscles relax. So that's the whole thing about getting this actin available. Now let's talk about calcium's moved it out of the way. Let's talk about the contraction cycle now. What does myosin do to interact with actin? So here it is in all of its glorious wonders. Let's go ahead and start off over here. Let's say that ATP is now binding on, so here's the myosin, here's actin. You can see that calcium is bound to troponin and tropomyosin is out of the way. ATP comes along and interacts with a piece of the myosin head. ATP causes the release of, if myosin were to have been bound to actin, it would have released it, and then it moves on and progresses, and it changes or modifies that ATP into ADP with a P. Now, where this P came from, you have to understand what ATP and ADP mean. Adenosine triphosphate is this, and adenosine diphosphate. Tri means, well, 3. Di means 2. P means phosphate. P means phosphate, and this P means phosphate. So what this is saying is you have just pulled off a phosphate from this ATP and have converted it into an ADP, but you haven't let go of that phosphate yet. Because this happens, notice the orientation of the myosin head at this point. It has click, 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 oriented upwards, nice and proud. The next stage that happens is that myosin head will then begin to interact with that actin binding site. And once it does that, and it releases that extra phosphate, the orientation of that myosin head changes and actually causes it to bend, kind of like it was bent here. But since it's now connected to actin, it kind of does like a paddling motion when you're rowing a boat, and it forces that actin towards that inner space, that H zone. You can reset this by changing out ADP with ATP, and ATP will cause that myosin head to release, and you go through the whole process again. Now, question. Do you think everything is released when one myosin head? Will all the myosin heads release if just one ATP binds onto one myosin head? No, because then you would have a useless muscle. You'd only be getting twitches going on, just like little bops. So it's really neat and interesting concepts. With that, this is an abbreviated thing. We got ourselves, again, that acetylcholine, interacting with the sarcoplasmic reticulum, popping open this calcium out into the wild blue yonder, interacts with the troponin, which allows myosin to interact, and voila, c'est magnifique. So what goes on here is that your muscle stays toned. You're going to try and stay within a certain range. So that myosin has somewhat of an interaction all the time when you're standing or what have you. And pretty much all you need to know about this is what I just told you. That tension has to be maintained to a certain degree. You don't want to over-tense it. You don't want to, because it's just plain useless. It doesn't get as much effort out. You want to contract it to a certain degree, and only to a certain degree. This is your optimum power, the optimum tension strength here. With that is the end. We'll be talking about muscle metabolism next, as well as some other miscellaneous items in part 3.